My dear students, this is Sandya Bandari, chemistry lecturer, TSWRDC Jagadgirgutta College. Now in this video, I am going to talk about square planar complexes. What is the substitution reaction in them? So I am going to discuss this in detail. This is very helpful for your for BSc final year students. In detail I am going to explain. Dear students, in substitution reactions of square planar complexes, first of all, you have to understand what is square planar complex and what hybridization it contains. There is coordination number 4 for square planar complexes. Similarly, in tetrahedral complexes, the coordination number is also 4, but hybridization is different in them. In square planar complexes, the hybridization is dsp2 hybridization, and in tetrahedral complexes, the hybridization is sp3 hybridization. In general, platinum, palladium 2 complexes, nickel also, and arum 3, rhodium 1, iridium 1. These type of elements, ions, metal ions, which consist of D8 configuration, follow the formation of square planar complexes with ligands. When you come to this hybridization, how the dsp2 hybridization for square planar complexes is obtained. Let's take the D8 configuration. 3D, the valence electronic configuration of, suppose nickel. All these elements, they have D8 valence electronic configuration. 3D8, 8 electrons are arranged like this, 4s is empty, 4p is also empty. This is the ground state electronic configuration of the corresponding metal ions. In presence of strong field ligands, the electrons will be paired up against the repulsive forces caused by the ligands. The strong field ligands can rearrange the electrons. The valence electrons, the unpaired electrons will be paired up. After pairing, the valence orbitals d orbital, s orbital and 2 4p orbitals, that is 3d orbital, 4s orbital and 2 4p orbitals undergo dsp2 hybridization. These 4d-sp2 hybridized orbitals will be oriented in square planar manner. So the ligands will be approaching towards the central metal for such kind of metal ions and form square planar complexes. Now let's discuss how the substitution reactions possible in square planar complexes. It is somewhat different from the octahedral complexes. There in this you are also going to see what is trans effect, how it would be helpful in our daily life. Now when you come to this substitution reaction of square planar complexes. Now let's take a general example with platinum metal ion, the ligands ammonia and chloride. Here 4 ligands are there. Ammonia is one of the ligand and chloride is the ligand. Let's assume Y ligand, a negative ligand, is going to substitute one of the ligand in them. Usually ammonia and ammonia related ligands do not cleave easily. Otherwise the ligands, unlike ammonia ligands, can be cleaved easily like negative ligands. So I am showing in this video, by taking this platinum complex, chlorine will be replaced by a negative ligand. Let's assume it is Y minus. Now the mechanism of square planar complexes substitution reactions, it follows 2 types of paths. One is solvent path and another one is displacement path. Solvent path, in solvent path, the solvent is usually water can substitute this chloride ligand first, and then in the next step the H2O will be replaced by the incoming ligand, freshly entering ligand, that is Y minus. The second step is a fast step. Now in the first step it is a slow step, which is rate determining step. Okay. But when you come to this displacement path, the displacement path follows associative type of mechanism. Now association means the entering ligand will associate with the complex. As a result, the intermediate, which is with the 5 coordination number, is formed. This 5 coordination number complex, which is an intermediate in this, is unstable and can easily replace that chloride ligand, because when the ligand Y with a negative charge or a pair of electrons is entering towards the platinum, the bond platinum and chlorine will be cleaved, because the bond will be weakened due to repulsive forces. Now after that, the chloride will be cleaved and the resultant complex is formed. When we come to the point factors affecting rate of substitution in square planar complexes, there are several factors which can affect the rate of reaction. First one, it is nature of the entering ligand. So it depends mainly on the nucleophilicity of the ligand. So nucleophilicity means being like a nucleophile. Nucleophile, it carries negative charge and it is acting as a ligand. So if you see the nucleophilicity order, so the methanol is acting as a ligand because oxygen can bond with the central metal, like that it is acting as a ligand, and it is very less nucleophilicity, and then chlorine, chloride, and then ammonia, and then nitrite, and then bromide and iodide. So here in this series, this thiosulfite complex has the highest nucleophilicity. So if the nucleophilicity increases, the rate of substitution reaction also increases. As the size of the negative ion increases, the nucleophilicity also increases. Then nature of the leaving group. So nature of the leaving group or leaving ligand depends upon the electronegativity. Suppose chloride has electronegativity, but it doesn't form a pi bond like cyanide or nitro group. Here these ligands, cyanide, nitro and carbon monoxide ligands, form a pi bonding with the central metal. Pi bonding means the central metal carries electrons, can be shared with the ligand. So these ligands can accept electron density from the central metal, like that a double band character is formed between the ligand and metal. If double bond character is formed, then the ligand cannot be easily cleaved. So in another words, this chloride will be cleaved fast than the cyanide. So the rate depends upon the nature of the ligand, which is nature of the leaving group, means it is already attached to the central metal. And another one, the other groups also influence the rate of reaction. Suppose let's take L ligand. So L, let us assume a ligand which is attached to the platinum, and chloride ligands, ammonia ligand. Suppose we want to replace one of the chlorine atoms ligands here. So the cleavage of these chlorine atoms will depend upon the ligand L, which is attached to the platinum. Now in some cases, the chlorine which is cis to the ligand and which is trans to the ligands will be replaced. So that is actually called as trans effect. So trans effect will be discussed in later after the completion of these factors. So now when you come to let's choose three ligands here. This is ethylene ligand, nitrite ligand, and bromide and chloride also. If you take this, if in place of L, if chloride is, if ethylene is there, suppose, it has high trans effect. Trans means the group which is trans to the, that is this chlorine atom, will be cleaved and form a trans compound. Now this is depending upon the, usually that it means the nature of the other groups also will affect the rate of substitution reaction. Another factor, effect of solvent also. The rate of reaction increases as the coordinating ability of the solvent increases. Coordinating ability. Here DMSO means dimethyl sulfoxide. This dimethyl sulfoxide is non-polar mostly, so it cannot easily coordinate to the central metal. So the solvent also will affect the rate of reaction. What I told here, rate of reaction increases as the coordinating ability of the solvent increases. Next, effect of central metal ion. Suppose in the metal ion participate in the formation of 5 coordinated complex, and in some cases means associative mechanism, and in some cases dissociative mechanism. I told you in square planar complexes it follows associative mechanism, that is in intermediate 5 coordinated complex is formed. If a metal ion which can easily form 5 coordinated complex, so then the rate of reaction increases. So that means overall the associative mechanism it follows in substitution reactions. Now let us discuss about trans effect. As I told you in the factors affecting the other groups which are present in the metal complex, that's one of the factor which can affect the rate of reaction. Now if you choose a complex with a nitro group as the nitro group as the center ligand, and chloride ions are the ligands. Suppose if you want to substitute a ligand, I told you that NO2 is a pi accepting ligand. Chloride are generally a negative ligands which are not formed a pi accepting ligand with the platinum, a bond with the platinum. When ammonia is substituting in this complex, now chloride will be substituted. Suppose if the chloride which is cis to the nitro group and also trans to the nitro group. So now in these two complexes there is an ability to form two complexes, but if you see the electrochemical series, this is cyanide, carbon monoxide, nitric oxide, these three ligands have high trans effect than the other followed. So in this case, when this nitrito group is attached to the platinum, usually the trans ligand will be substituted. So in these two complexes, trans compound is major compound than the cis. When you come to this, why this cyanide, carbon monoxide, nitric oxide have high ability of trans effect? So because they have ability, pi bonding ability with the ligands, with the central metal. So these ligands have greater trans effect. That means suppose a metal which has d orbital, the electron density present in the central metal can be accepted by the suppose carbon monoxide. So it has a empty p orbital, the electron density is shared from the metal to the ligand. So there is a double bond character is formed, the electron density is moving from the central metal to the ligand. So the strong bond is formed in general. So the which is trans to this ligand can be easily cleaved. So which can be explained, the mechanism, the whole mechanism will be explained in the theories. I will in this video in continuation. Dear students, in the next video I will discuss the continuation, the trans effect, the theories to explain the trans effect, why only the trans compounds are major in the substitution reactions of square planar complexes. Thank you.